Hello my dear students, welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today I am going to teach you Heisenberg Uncertainty Principle. You can see the picture of Heisenberg sir on the screen. So let us start. This principle states that it is impossible to determine simultaneously with precision both the position and the momentum of any subatomic particle. Subatomic particles like electron, protons, neutrons. So let me write this thing for you. This principle states that I'm writing this principle states that it is impossible to determine simultaneously. Very important word is simultaneously. It is impossible to determine simultaneously with precision both the position and momentum of any subatomic particle, that is electrons, protons or neutrons. Now we cannot find both the position and momentum of any subatomic particle simultaneously. That's the Heisenberg uncertainty principle. So let's talk about, first of all, we will have the error in calculating the position and the momentum. So let's talk about, first of all, error or uncertainty in measuring the position of electron. The very first point is we are talking about error or uncertainty in measuring the position of electron. Error or uncertainty in measuring the position of electron. The error or uncertainty in measuring the position of electron is represented by a symbol called delta X. Now, let's talk about it. The electrons are almost dimensionless. So whatever wavelength of photon we use for an atom, it will appear as the uncertainty in the position of the electron. The electron will move a distance which is equal to the wavelength of the photon which is striking that electron. So I'm writing the electrons are almost dimensionless. The electrons are almost dimensionless. So whatever wavelength of a photon we use, so whatever wavelength of photon we use will appear as uncertainty in the position of the electron. will appear as uncertainty in the position of electron. That means the electron will move a certain distance. That means the electron will move a certain distance when photon strikes it. When photon strikes it. And that distance moved by electron and that distance moved will be directly proportional will be directly proportional to the wavelength of the photon we used. Wavelength of the photon we used. Now, the distance moved by electron is actually the delta x. That's the uncertainty in the measuring the position of the electron. And now that delta x, the change in position or uncertainty in the position, will be directly proportional to the wavelength of the photon that we have used in our experiment, or the photon that strikes the electron. So now let's talk about the second point: error or uncertainty in measuring the momentum of electron. Now the second point is error or uncertainty. Error or uncertainty. Error or uncertainty in measuring the momentum of electron. In measuring the momentum of electron. Error or uncertainty in measuring the momentum of electron. Now, first of all, momentum is represented by a word small p. The momentum is equal to the mass into velocity. Now, the mass of any subatomic particle will remain constant. That is, the mass of any subatomic particle, that is like electron, proton, neutron, it will remain constant. So there will be a change in the velocity of that particle, which will change the whole momentum of that particle, and that's the uncertainty in the momentum. So uncertainty is in momentum is represented by a symbol delta p. Now I'm writing when the photon strikes the electron. When the photon strikes the electron, comma, it imparts all its energy to the electron. It imparts its all energy to the electron, which changes the velocity and finally changes the momentum of electron, which changes the velocity of electron and finally changes the momentum of the electron. Now, let's talk about it. That means the change in momentum will be directly proportional to the energy of the photon. Now, on the another hand, we know the formula for the energy of photon, and it is equal to the hc by lambda, which is the wavelength. That means the energy of photon is inversely proportional to the wavelength of the photon. So that means energy of photon is inversely proportional to wavelength, which signifies that change in momentum of any subatomic particle will be inversely proportional to the wavelength of the photon which strikes that particle. Now, we got the two cases, that delta x is directly proportional to wavelength and the delta p is inversely proportional to wavelength. So let me make two cases. So let's talk about two cases. The case number one. Case number one, let's take the wavelength of photon to be very minimum to determine the position with the minimum error. Let's take the wavelength of photon to be very minimum, to determine the position of electron, to determine the position of electron with minimum error. With minimum error. So let's talk about it. We know that the change in position of electron is directly proportional to the wavelength of the photon which is striking that electron. If we take this wavelength to be very minimum, we will also get the uncertainty in the position of electron to be very minimum. But due to which what will happen? We also know that the change in momentum is inversely proportional to wavelength. If we take wavelength to be minimum, because of inverse proportionality, the change in momentum will be maximum then. So it signifies that we cannot find the position and the momentum of the electron or any other subatomic particle simultaneously. So let's talk about the another case. So in this case we got that if change in position, if uncertainty in the position is minimum, then the change in momentum will be the maximum if we take wavelength to be the minimum. Now let's talk about the case number 2. Let's talk about case number 2. Case number 2. Now let's take the wavelength of photon to be maximum to determine momentum with the minimum error. Now let's take wavelength of the photon. Let's take wavelength of photon to be very maximum, to determine the momentum of electron, to determine the momentum of electron with minimum error, with minimum error. So we are taking the wavelength of photon to be very maximum to determine the momentum of electron with a minimum error. That means, first of all, what I'm trying to do, first of all, we know that the change in momentum is inversely proportional to the wavelength. If we are taking the wavelength to be the very maximum value, because of inverse proportionality, the change in momentum will be the minimum. So on the other hand, then what will happen? Now we know that change in position is directly proportional to the wavelength. So if this wavelength is maximum, then the change in position will be maximum because of direct proportionality. So again, this thing proves that we cannot find the position and momentum of electrons simultaneously, because if we find the momentum with a minimum error, then we will get the maximum error in the position. So what next? Let's calculate the maximum minimum error that we will get during any calculation. So I'm writing minimum error. So I'm writing minimum error in calculating position and momentum of electrons simultaneously. Minimum error in calculating position and momentum of electron simultaneously. Now what we have just done, delta x directly proportional to wavelength. Now delta x is equal to the k into lambda, where k is the proportionality constant. Now delta p was inversely proportional to wavelength, then delta p will be equal to the k dash by lambda, where k dash is again proportionality constant. Mark it as number 1 and mark it as number 2. Now on multiplying the number 1 and the number 2, delta x into delta p will be equal to the k into lambda into k dash by lambda. Here what will happen? This wavelength got cancelled with the wavelength, and what you are left with, delta x into delta p is equal to the k into k dash, and Heisenberg sir has found the value of k into k dash to be h upon 4 pi, comes out to be delta x into delta p. So Heisenberg sir told that the minimum error, delta x into delta p, the minimum error in calculating position and momentum of electrons simultaneously will be greater to or equal to h upon 4 pi. So what next? Now delta x was delta p is m into delta v. It will be greater than or equal to the h upon 4 pi. So this is the Heisenberg uncertainty principle. In the next video, we are going to do some numericals on this topic. I hope you all understood today's lecture. If any student wants to book a paid online one-to-one class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please like, subscribe and share my channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.